So this week we're starting probability. So today is going to be kind of an intro to probability, get some basics down. So number 1 says using the spinner given to the right, answer the following questions. Part A, find the probability of spinning an even number. And we show that as P parenthesis even. So this P means the probability, and even is what we want. It is the probability of what we want. So probability of getting an even. Looking at the spinner, there are 5 sections. Each one is the same size. Evens, we have the numbers 2 and 4. So there are 2 evens out of the 5 spaces. So the answer to A should be 2/5. Part B, find the probability of not spinning an even number, which we would say P of not even, the probability of not even. Well, those were the leftover numbers, 1, 3, and 5. Those are the non-even numbers. So there are 3 out of the 5 that are not even. So the answer to B is 3/5. So any happening whose result is uncertain is called an experiment. Now, if I were to spin the spinner, I really don't know what it's going to land on. So the act of spinning the spinner is considered an experiment. The next definition says the possible results of the experiment are outcomes. So for example here, one possible result would be to spin a 3. So that 3 is considered an outcome. Next, the set of all possible outcomes of the experiment is the sample space of the experiment. For example, all the possible outcomes on that spinner, I could get a 1, I could get a 2, I could get a 3, I could get a 4, or a 5. This is considered my sample space. These are all my possible outcomes when I spin that spinner. And then last, any sub-collection of a sample space is an event. For example, my evens. This is considered an event. The probability of getting an even, that is the event that I was looking to have happen. So my evens, we had 2 and 4. There were 2 of them in that event. So with these terms in mind and what we did in question 1, here is your definition of probability. It says the probability of an event E occurring is given by the ratio P of E, meaning the probability of event E, is equal to N of E divided by N of S. So N of E is the number of outcomes that fall into the event E. For example, if E was my evens, A from above, N of E would be 2 because there were 2 outcomes that fall into that event of being even. N of S is the number of outcomes that fall into the sample space. So my sample space, if we look at that third bullet up above, there were 5 possible outcomes. So N of S would be 5. So then putting it together, the probability of that event E, it says is N of E, which is 2, over N of S, which is 5, so 2/5. So you probably already knew how to do this for probability, but this is the formal definition. So that's just so you have it. So now, given the above definition and looking at examples 1, A and B, between what 2 numbers must all probabilities lie? And I want you to explain. So all probabilities should fall between 0 and 1. Now, a lot of times we do use fractions. We could also use decimals. You might have also have seen probability done with percents. So we could also say between 0% and 100%. Decimals and fractions would use the 0 to 1. So what this means, the 0 means that it won't happen at all. For example, the probability of getting a 6 on that spinner at the top of the page. That's not going to happen at all. There are 0 spaces that have a 6 in it out of the 5. And 0 divided by 5 is just 0. So this means that it will not happen at all. The 1 means that it will definitely happen. So an example, the probability of a number less than 6 on that spinner above. Well, all the spinner sides, all those spaces were less than 6. So 5 out of the 5 spaces fit this criteria. And 5 out of 5 is 1. So all probabilities are going to fall between these two numbers. So now let's take a look at another example. Number 2 says, consider the spinner shown below that has been divided into 8 equally sized sectors of a circle. The spinner is spun once. In this experiment, we will let A be the event of landing on an even, and B is going to be the event of landing on a prime number. So first, let's figure out what would be the outcomes in these events. So event A, what would be my sample space? What would be my outcomes that fit here? Well, A is that it is even. So looking at this spinner, the numbers that fit that criteria would be 2, 4, 6, and 8. So there are the possible outcomes for event A. Event B, this is that it is a prime number. Prime numbers are numbers that are divisible by 1 and themselves. The number 1 is not considered a prime number because it's only divisible by 1 and itself, but that is the same number both times. It has to be 1 and itself, where the itself is different than the 1. So the number 2, that is prime because it's divisible by 1 and 2. 2 different numbers go into it, and those are the only 2. The number 3 is prime. It's only divisible by 1 and 3. 4 is not. It is divisible by 1 and 4, but it is also divisible by 2. So because it's divisible by something else other than 1 in itself, it is not prime. 5 is prime. 6 is not. 7 is prime. And 8 is not. So these are the possible outcomes for event B. So it says here, fill in the Venn diagram below with the actual numbers from the spinner. So Venn diagrams, I'm sure you have seen these in other classes. Notice we have 2 circles here. Above the circle on the left, it says A, which was event A, the evens. Above circle B, it says primes. That was event B, the prime numbers. And they are enclosed in this big rectangle that has an S, which means the sample space. That is all the possible outcomes. So the numbers 1 through 8. So within this rectangle, all 8 numbers have to fall. Now, notice the 2 circles overlap in the middle. That is what they have in common, what sits in both circle A and circle B. So looking at my 2 lists, notice the number 2 sits in both lists. So the number 2 would go right in that center overlap piece. Now, the numbers 4, 6, and 8 in A do not show up in B. So all 3 of those numbers are going to go in circle A, but not in the part of circle A that is shared with circle B. Similar, the numbers 3, 5, and 7 from set B. They are part of B, but they don't show up in A. So those 3 numbers have to go into circle B, but not the part of circle B that is shared with A. Now, looking there, we have the number 2, we have the number 3 within a circle, 4 is there, 5 is there, 6 was listed, 7, and 8. All of those numbers were listed within those 2 circles. We're still missing the number 1, though. The number 1 does not fit in either circle, but it is still part of our sample space because it is a possible outcome on the spinner. So the number 1 is going to go into the rectangle, but not in one of the circles because it does not fit those criteria. So this is how the Venn diagram works. I'm going to use this Venn diagram to help us with the next part. So it says a set is a collection of things that satisfy a well-defined criteria. When we have 2 or more sets, we can talk about their union and their intersection. Their technical definitions are given below. For 2 sets A and B, so we had sets A and B above, A was even, B was prime. Their union, we use the word or to represent union, or the symbol that looks like a giant U. This means everything that is in A or B, just anything that fits within at least one of those 2 circles or both. Whereas the intersection, which we use the word and or an upside down U to represent intersection. Think about an intersection of 2 roads. It is where the roads overlap. So the intersection is the part of the circles. See, there's the rest of our circles. It is the part of the circles that overlap each other. That is their intersection. So looking back at our Venn diagram from above, if I wanted to find A or B, if I wanted to list out the numbers that fall into A or B, their union, it just means that it has to be a number that falls into those circles. It could be anywhere in those circles for union. It could be in just circle A, just circle B, or the part where the circles overlap. As long as it's fitting inside of those circles, at least one of them, it is part of this union. So that would be the numbers 2, 3, 4, 5, 6, 7, and 8. Each of those numbers fell into at least one of those circles. Part B, A and B, their intersection. What fell into their intersection? Well, that was the number 2. The number 2 was in where the two circles overlapped. So that is their intersection, which we say A and B. So now, number 4, consider this equation. N, the number, remember this means the number of things in A or B. Is it equal to the number of things in A plus the number of things in B? Well, let's take a look. The number of things that were in A or B. If I go back and count, I had 1, 2, 3, 4, 5, 6, 7 things were in their union A or B. Is that equal? So I'm checking, is this equal to the number of things in A? So looking back, the number of things in A, I had 1, 2, 3, 4 things in A. The numbers 2, 4, 6, and 8. Plus the number of things in B. So looking at B, I had 1, 2, 3, 4 things in B also, 2, 3, 5, and 7. And if I take a look and actually add those two together, I get that 7 is equal to 8. So no, that is not true. And why? Why is that not true? Why did that not come out right? If union just means I'm taking everything all together and putting it together, why couldn't I just add the number of things that were in each one separately to figure out how many things would be in the union? Well, the issue was the number 2. This number got counted twice. The number 2 was in set A, but it was also in set B. So when I counted up how many things were in each, I counted the number 2 twice. It fell with my first 4, and it was counted with my second 4 here. So in order to make this true, in order to figure out the number of things in the union of two sets, you want to take the number of things in each one separately, add them together, but then subtract the number of things in their intersection. There was one thing in the intersection of these two sets, the number 2, that's one thing. So if I had subtracted that off, 8 minus 1, I would have gotten that 7. So you should know this formula. It is going to come up when we do these questions. So last thing we're going to look at here. This is a two-way frequency chart, and it gives us a great example of how events or sets can combine the union and the overlap, the intersection. So let's take a look at this and develop some ideas about probability along the way. So number 5, a small high school surveyed 52 of its seniors about their plans after they graduate. They found the following data in the table and wanted to analyze it based on gender. So notice in the table, we have 2 rows, well 3, but 2 here. First row means that you are going to college, which if we take a look, we're going to use the letter C to represent that. And then the second row means that you're not going to college, and we're going to use the N to represent that. Then the top, I have a few columns here. Being male, we're going to use the letter M to represent it. And being female, we're going to use the letter F to represent it. So these are the different events that we have. Notice at the end of each row and column, we have their totals. So if you added up the number of students going to college, 16 plus 13, there's a total of 29 going to college. Not going to college, 14 plus 9, there's 23 of them. And then the big total, I usually call this the total, there's 52, which makes sense because they said that there were 52 seniors that were surveyed. So part A here says, based upon the table above and the aforementioned variables, that's C and M and F that we used, give the values for each of the following. So first one, N of M. That N again means the number. So the number of outcomes that fit into event M, which is being a male. So the number of students that were male. Now, I don't care right now for this question if these are males who are going to college or not going to college. I just want the number of students that were male in general. So I'm looking at the total of males, which is 30. So see here, these are my males. The total is 30. You do not have to add up all three of these. That last one is already giving you the total. So the adding was already done for you. Second one, N of F, the number of students that were female. So looking at my females all together, that total was 22. Third one, N of C, the number of students going to college. So we're now looking at that row. College total was 29. Fourth one, N of N, the number of students not going to college. That is this row that we are looking at. That total is 23. Okay, next one, fifth one. The number of students that were male and going to college. This, remember, is their intersection, the word "and." If you go back to the page before, the word "and" was intersection. So we're looking at male and going to college. So the intersection where they overlap is right here, and it is the number 16. So there are 16 students who are male and going to college. Okay, next one. The number of students who are F, and then there's the upside down U, which again, if you go back to the page before, this means intersection again. So again, I'm looking for the overlap, but this time the overlap of female and going to college. So that overlap is at 13. And then last, the number of students that are female or going to college. So again, this is the intersection. And if you remember, at the end of the last page, we came up with a formula to figure out this number. So the formula said that you're going to do the number of each one separately, but then from that, we need to subtract the number in the intersection, because again, remember that whichever students fall into both the female and the college category, those students are going to get counted twice. So the number of students that were female, that was the second one we did, 22, plus the number of students going to college, that was the third one we did, 29, minus their intersection, the students that were both female and going to college. So that's the very last question we did, the 13. So adding and subtracting, we get 38 total students are either female or going to college. So part B, what is the probability that a person picked at random would be a female who is going to college? Represent this as a union or an intersection. So which one are we dealing with? Well, we are looking for the probability of female who is going to college. So union would just include everyone who was female and everyone who was going to college. But for this question, I don't want everyone. I want the females who are going to college. So that means I am looking for their intersection, the probability of their intersection. So how many students fit that criteria? Well, that was the sixth one we did. 13 students fit that criteria. Out of our total, how many total students are there? There was a total of 52. So the answer is 13 over 52. Now, you do not have to simplify these. That is the nice thing about probability. You can if you want, but you do not have to. If you do, you can use your calculator, type it in, 13 divided by 52, math, enter, enter to make it a simplified fraction. Or if it's a nice decimal, give a decimal. This would be 0.25 or 1/4. That does work also. But the nice thing about probability, like I said, you could just pull the numbers out, put them into a fraction, and then just leave it. C, what is the probability that a person picked at random would be a female or someone going to college? Represent this as a union or intersection. Well, the word or is a nice big giveaway here. We are looking for the probability of a female or going to college. So that means on top, I need to know the number of things that fit in this category. So the number of people that were female or going to college. That was that last one that we did up above. That was 38. Out of the total, there are 52 students. So my answer is 38 out of 52. Part D, explain why that probability we just found, 38 over 52, is not equal to the probability of being female. So the probability of being female would be 22 over 52, plus the probability of going to college, which would be 29 over 52. So now if you did add those together, you would not, in fact, get 38 over 52. You would get 51 over 52, which is not right. So explain why. Well, same reason for what we were doing before on the end of the last page. It includes the females going to college twice. So when I found that probability of female, 22 over 52, and then that probability of going to college, 29 over 52, I included those female students who were going to college twice. They got counted in each probability. So just like that last formula that we did before, which we used up here, finding the number of things in the union, the or, it's going to be a almost identical formula for the probability of the union or the or. You can find the probability of each event separately, but then you want to subtract from them the probability of their intersection, because whatever is in both is going to get counted in each probability twice. Let me know if there's any questions. Send me a message on Google Classroom or an email, and I'll be happy to help.